cycle of life depends on the soil. Without good soil, threats can be seen. Our lives depends on the soil. It is one of the major components to achieve basic needs and the development of one's country. That's why this topic is important. To learn more about this topic, please keep on watching. Good day everyone, we are the Group 7 of Engineering 1D and today we're going to discuss about the soil chemistry. But first, allow me to introduce the group members. We have here Miss Catricia Ann Salcedo, Miss Katrina Shane De Castro, and Miss Perlina Buyabor. And the learning objectives of this report are the following. First is to know the concepts of soil, learn the history, be familiar with compositions and properties, know how soil forms, and lastly, know the importance of soil.
Hello everyone, I'm Patricia Ann Salcedo. What is soil chemistry? Soil chemistry is the branch of soil science that study the chemical composition, properties, and reaction of the soil. It composed of air, water, inorganic and organic solids, and microorganisms. Chemical reactions and processes take place between the phases, such as carbon dioxide in the air combined in water counteracting the inorganic solid phases. Plant growth and water quality are both influenced by chemical reaction between soil solids and soil solution. Soil chemistry is traditionally focused on chemical reaction that occur in soils and influence plant growth and nutrition. In 1970s and 1990s, concern about metal, metalloids, nutrients, and organic contaminants in soil grew. Environmental soil chemistry is a study of chemical reaction or processes between soil and environmentally important plant nutrients, radionuclides, metalloids, and organic chemicals. Environmental soil chemistry illustrates fundamental principles of soil chemistry with respect to environmental reaction between soils and others. Environmental soil chemistry knowledge is essential for predicting the fate of contaminants in the surface and subsurface environment. It involves understanding the chemistry and mineralogy of organic and inorganic soil components, which can have impact on the solubility, mobility, speciation, toxicity, and bioavailability of contaminants. It also useful for making sound and cost-effective decisions about contaminated soil remediation. And now, let's talk about history of soil chemistry. Soil chemistry can be considered as natural composition of the given soil. This natural composition of a soil is a function of that soil's parent material. In many areas of the world, soil is formed in place and derived directly from the weathering and degradation of the rocks. When soil is derived from the rocks, it's soil chemistry. It is the direct reflection of the rock chemistry, including the minerals found in the rocks. It all started with the research of J. Thomas Way, a consulting chemist to a Royal Agricultural Society in England. In the early of 1850s, Way was known as the father of soil chemistry. He conducted a series of groundbreaking research in the ability of soils to exchange ions. He discovered that soils could absorb both cations and anions as well as exchange ions to other ions. He recognized that ion exchange was quick, that clay was an important soil component in cations absorption, and that heating and treating soils with strong acid reduced the ability of the soils to absorb ions. The vast majority of Way observations were ultimately confirmed to be right, and his work provided a framework for several critical soil chemistry research on ion exchange and absorptions. We researched influence a wide range of fields including chemical engineering and chemistry. Regardless of who we are and where we live, the chemical processes that occur constantly in soils are essential to our survival. The majority of individuals are interested in soil chemistry because they want to ensure and boost the food and crop output. Human nutrition comes mostly from the soil and will continue to do so. Terrestrial plants are still the most cost-effective and efficient way to turn solar economy and national well-being. Plant growth is influenced by a variety of factors, including soil chemistry. The availability of essential main elements, including nitrogen, phosphorus, sulfur, potassium, calcium, and magnesium, as well as trace elements including boron, copper, iron, manganese, molybdenum, and zinc, is regulated by soil chemistry properties. These are all essential because of the plant must have these elements in order to progress through its physiological stage of its growth cycle. In contrast to climate and other uncontrolled variables, agriculturists could significantly influence and modify soil chemistry. Soil chemistry can help reduce the toxicity of materials that may affect plant growth. Good day everyone, my name is Katrina De Castro and today I will tackle about the components and properties of soils. So the first composition of soil is minerals. Mineral is one of the parts of soil composition including humus, living organisms, water, and air. Minerals are a very essential substance found in soil. It is the largest component of the soil, making up almost 40 to 45% of the total components. Soil is rich in minerals such as iron, phosphorus, calcium, magnesium, sulfur, and etc. Minerals constitute the major portion of soil. Minerals are necessary for plant growth and development. The minerals present in soil are absorbed by plants through the roots. For example, nitrate is an essential mineral as it helps in the synthesis of proteins. Magnesium is an important component of chlorophyll. The mineral soil is very supportive of plant growth. It also helps the soil highly rich in nutrients and make highly fertile, which gives better crop result and increases economic development. So the next composition is soil organic matter. The soil organic matters are composed of three things: the living, the dead, and the very dead. First, we have the living. This part of soil organic matter includes a wide variety of microorganisms such as bacteria, viruses, fungi, protozoa, and algae. Sticky substances on the skin of earthworms and other materials produced by fungi help bind particles together. In addition, they recycle plant nutrients. Sticky substances on the skin of earthworms and other materials produced by fungi help binds particles together. This helps to stabilize the soil aggregates, which are clumps of particles that make up good soil structure. Sticky substances on plant roots, as well as the proliferation of fine roots and their associated mycorrhizae, help promote development of stable soil aggregates. The next one is the dead. The fresh residues or dead organic matter consist of recently deceased microorganisms, insects, earthworms, old plant roots, crop residues, and recently added manures. In some cases, just looking at them is enough to identify the origin of the fresh residues. This part of soil organic matter is the active or easily decomposed fraction. This active fraction of soil organic matter is the main supply of food for various organisms, microorganisms, insects,
and earthworms living in the soil. Their structure makes them easy to decompose because so many microorganisms use them as food. Some cellular molecules such as lignin are decomposed because it takes longer for organisms to do so. This can make up a large fraction of soil organic matter in poorly drained soils like pits and mucks, as well as wetlands that have been taken into agricultural production. These hold large amounts of organic matter that was not decomposed due to waterlogging, but they don't provide the same benefits as the fresh residues. The last one is the very dead. This includes other organic substances in soil that are difficult for organisms to decompose. Some use the term humus to describe oil soil organic matter. We'll use the term to refer only to that relatively stable portion of soil organic matter that resists decomposition. Humus is protected from decomposition mainly because its chemical structure makes it hard for soil organisms to utilize. The next composition of soil is the gas. Soil gas is vapor that can be extracted from the subsurface from pores in unconsolidated material above the water table. In uncontaminated areas, it is usually a mixture of atmospheric gases such as oxygen and nitrogen, and gases such as carbon dioxide produced by metabolic activities of soil zone organisms. The last composition of soil is water. Soil water contains nutrients that move into the plant roots when plants take in water. Water enters the soil through large pores, macropores, and is stored in many small pores, micropores. Porous soils have a balance between macro and micro. So now let's move on to the soil properties. The first one is texture. Soil texture has an important role in nutrient management because it influences nutrient retention. For instance, finer textured soils tend to have a greater ability to store soil nutrients. The next property of soil is the structure. Soil structures is the arrangement of soil particles into groupings. These groupings are called beds or aggregates, which often form distinctive shapes typically found within certain soil horizons. Soil aggregation is an important indicator of the workability of the soil. Soils that are well aggregated are said to have a good soil tilth. The next property is porosity. Porosity is the pore space between soil mineral particles and solid organic matter filled with either air or water. The pores between both contains and controls most of the functions of soil. It is not just the total amount of pore space that is important, but the size distribution of the pores and the continuity between them, which determines function and behaviors of soil. The last property of soil is the color. Soil color is one of the indicators of soil status and depends on many factors, mainly on the amount and state of organic matter and iron oxide, as well as amount of air and water in soil pores. In general, dark soils have high organic matter content. Gray soils are waterlogged or anaerobic. Brown soils are well-drained and aerated soils. And now let's move on to the different type of soils. The first one is sandy soil. Sandy soil is light, warm, dry, and tends to be acidic and low in nutrients. Sandy soil are often known as light soils due to their high proportion of sand and clay. Clay weighs more than sand. These soils have quick water drainage and are easy to work with. They are quicker to warm up in spring than clay soils but tend to dry out in summer and suffer from low nutrients that are washed away by rain. The next type of soil is the clay soil. Clay soil is a heavy soil type that benefits from high nutrients. Clay soils remain wet and cold in winter and dry out in summer. These soils are made up of over 25% of clay, and because of these spaces found between clay particles, clay soils hold a high amount of water. Because these soils drain slowly and take longer to warm up in summer, combined with drying out and cracking in summer, they can often test gardeners. Silt soil. Silt soil is a light and moisture-retentive soil type with a higher fertility rating. A silt soil comprises of medium-sized particles. They are well drained and hold moisture well. As the particles are fine, they can be easily compacted and are prone to washing away with rain. By adding organic matter, the silt particles can be bound into more stable clumps. The next one is peat soil. Peat soil is high in organic matter and retains a large amount of moisture. This type of soil is very rarely found in a garden and often imported into a garden to provide an optimal soil base for planting. Chalk soil. Chalk soil can be either light or heavy, but always highly alkaline due to the calcium carbonate within its structure. As these soils are alkaline, they will not support the growth of ericaceous plants that require acidic soils to grow. The last type of soil is the loam soil. Loam soil is a mixture of sand, silt, and clay that are combined to avoid the negative effects of each type. These soils are fertile, easy to work with, and provide good drainage. Depending on their predominant composition, they can be either sandy or clay loam.
Good day everyone, my name is Prilina Buyabor, and for this part, I'm going to discuss on how the soil forms. So, how soils form. So, it takes a very long time to make soil, sometimes 1,000 years or more. So, it is formed from the weathering of the rocks. So, what is weathering? Weathering describes the breaking down or dissolving of rocks and minerals on the surface of the earth. Water, ice, acids, salts, plants, animals, and changes in the temperature are all agents of weathering. There are two types of weathering. First is the physical weathering. It is also called as mechanical weathering. It happens when physical forces repeatedly act on the rock. One example is rocks tumbling over one another, knocking off pieces from one another, and this often happen in a river, desert, or hillside. So the second type of weathering is the chemical weathering. The rock disintegrates or even dissolves because a chemical reaction changes the composition of the rock. When certain types of rock come into contact with rainwater, which is often slightly acidic, especially when there is pollution present, a chemical reaction occurs, slowly transforming the rock into substances that dissolve in water. So for this part, if you have ever looked closely at soils in different areas, you will know that they all look, feel, and smell different. These are the factors that creates soil. First one is the climate. Soils vary depending on the climate. Temperature and moisture amounts cause different patterns of weathering and leaching. Wind redistributes sand and other particles, especially in arid regions. The amount, intensity, timing, and kind of precipitation influence soil formation. Seasonal and daily changes in temperature affect moisture effectiveness, biological activity, rates of chemical reactions, and kinds of vegetations. The second one is topography. Slope and aspect affect the moisture and temperature of soil. Steep slopes facing the sun are warmer. Steep soils may be eroded and lose their topsoil as they form. Thus, they may be thinner than the more nearly level soils that receive deposits from areas upslope. Deeper, darker colored soils may be expected on the bottomland. So the third one is biological factors. Plants, animals, microorganisms, and humans affect soil formation. Animals and microorganisms mix soils and form burrows and pores. Plant roots open channels in the soils. Different types of roots have different effects on soils. Grass roots are fibrous near the soil surface and easily decompose, adding organic matter. And taproots open pathways through deeper layers. Microorganisms affect chemical exchanges between roots and soil. Humans can mix the soil so extensively that the soil material is again considered parent material. The last one is time. Time is also a component for the other factors to interact with the soil. Over time, soils exhibit features that reflect the other forming factors. Soil formation processes are continuous. Recently deposited material such as the deposition from a flood exhibits no features from soil development activities. The previous soil surface and underlying horizons become buried. The time clock resets for these soils. Terraces above the active floodplain, while similar to the floodplain, are older land surfaces and exhibit more development features. And now, we are here on the last part of this report, which is the importance of the soil. So, why is soil so important? Soil is teeming with life. Soil is teeming with life. There are more living organisms in the handful of soil than there are people on the planet. Second one is soil provides a host of crucial services for both people and the planet. Soil puts food on our planet, purifies our water, protects us against flooding, and combats drought. It's also key to tackling climate change as it captures and stores vast amounts of carbon. The third one is there is no food security without healthy soils. Agriculture is the only essential industry, but farming has one of the biggest impacts on soil health. So, intensive farming eliminates species living within the soil, species that give soil its fertility. How we farm today is destroying our ability to feed the planet in the future. Lastly, creating new soil takes longer than the average human life. We need to protect and conserve soil. It is a living resource and it's finite. Lastly, creating new soil takes longer than the average human life. We need to protect and conserve soil. It is a living resource and it is finite.